Hey folks, our second video on rotational inertia is about extended objects. There's not much that you need to do yet with this concept other than understand that it exists. So I'll try and keep this a little brief. Extended objects are not point masses. So an extended object is an object that is either long or large, and its mass is distributed throughout the object. In AP Physics 1, every extended object has a uniform density, meaning the mass is distributed equally throughout the object. So its center of mass is always going to be at the direct center. Now, determining the rotational inertia of an extended object that takes up space requires the use of calculus. And since this is an algebra-based course, you are not responsible for determining the rotational inertia of an extended object. In your textbook on page 232, there are a list of pre-derived expressions for some common shapes. Before we look at that page, I want to stress in this course, you have to be aware that these exist. You must use them when they are provided, but under no circumstances should you memorize them. You will not need to do that. So here is page 232. On the left-hand margin, there's just a set of pictures. It says moments of inertia, iota, for various rigid objects of mass m. So there's moment of inertia instead of rotational. And what follows are a set of pictures, and they're categorized. So the first two are a cylinder or a hollow cylinder and a filled-in cylinder, a solid one, a thin rod around its center and around its end. So as we learned in the last video, one way to change the rotational inertia is to change the axis without changing how the object is arranged or the system. Then we have a solid sphere with the axis through the center and then with the axis tangent to the surface. That's a weird one. You don't see that one very often. And then a thin-walled spherical shell, so basically like a hollow, like a ball, like a tennis ball, with a very thin shell, thin outside, axis to the center, and then a rectangular sheet. And all of these expressions depend on the mass, m, and then one of the main dimension of the object, so the radius of the object or the length of the object. Now this capital R is actually the radius of the object. In physics, when you see like a lowercase r, that typically means the distance between 2 points and depends on the context. Whereas if you see a capital R, that is typically the radius of the object. So, if I put objects on this disk, they would have positions that are lowercase r positions, but the disk itself has a capital R radius. Anyway, that's the set of those. And again, you don't need those until you're given them in a problem. You don't need to know anything about them and just know about them. So one of the most important parts of this part of the unit is knowing what to do with objects and how to compare their rotational inertias. So we're going to take the most common example. Suppose a hollow cylinder and a solid cylinder have the same mass and radius. So the hollow cylinder is going to look like this, and it's going to have a radius r. It's going to have a mass m. And then you have a solid cylinder, and I'm going to try and make it the same size. It's going to be filled in because there's mass throughout it. It also has a radius r and then a mass m. The question is, which has a greater rotational inertia? And this is something that you are expected to be able to do without looking up an expression. As long as they have the same mass and radius. If they don't have the same mass and radius, you actually can't answer this question. But if the hollow cylinder is made of a much more dense material, then just this ring of it could have the same mass as this entire disk that is filled in. And I actually have a set of this in the classroom, so we'll do some demos with this, where you have a ring and a disk of the same radius and mass, and you can compare their rotational inertias. Now, the reason why you're expected to answer this is just because they have the same mass and radius, because I depends on mass and distance from the axis. And it's this distance from the axis that means the most. If they have the same mass, then the total particles weigh the same. The total number of like protons and neutrons is the same. And so what that means is for the hoop here, or hollow cylinder, all the mass is distributed around the outside. It's all located essentially at this distance, capital R. Whereas for this disk, the solid cylinder, the mass is distributed everywhere. There's a lot of mass that's really close to the axis, and then there's a lot of mass that's really far from the axis. That's what evenly distributed means. So the rotational inertia for the hollow cylinder is greater than the rotational inertia of the solid cylinder, because the hollow cylinder has its mass concentrated at a greater average distance from the axis. Said another way, hollow objects will typically have higher rotational inertia than solid objects of the same dimensions. And that's it for now. When we get into Newton's laws and then energy and angular momentum, we will work with some of these expressions. But again, if you need one of these expressions that you saw in the textbook, it will always be provided to you.